All right, so let me zoom into two marbles here to show you the details. Zoom in. Yeah, I think that's okay. So there is a time domain responsible for generating all randomly time-based signals like rhythms and gates. And this time domain is here on the left side. It's the rate, the bias, the jitter, and these two fancy little groups of colored LEDs with their button. There is a CV domain there, responsible for generating random voltages. It's on the right side here. It's the spread knob, the bias, once again bias, but it works differently from this one. Bias, steps knob, and again two groups of fancy little buttons and colored LEDs. And there is a general overall management of the randomness of each of the other two domains. And this is here above with these big knobs, sometimes green and sometimes gray, the déjà vu knob, the length knob, and the button again. But with this button, there's something special. All right, so in the time domain, so on the left side here, rate, jitter, bias, and these two groups of buttons and LEDs. In the time domain, the output T1 below here puts out a basic sequence of gates. Let me show this by simply, I don't want this. I'll reduce the zoom out a bit. A little bit more. View. Okay, come on. Yeah, that is okay. So I patch the output of T2, generating this basic rhythm, what I told you, and I patch the output to the gate output of this ADSR and the output of the VCA into the mixer in the middle. Yeah, this is the basic rhythm. The sequence is now divided between the outputs on the left and on the right, outputs T1 and T2. So let me use them as well. Now we hear additionally T1. Why don't we hear it? Ah, yeah, from time to time. Put up the bias knob. And now we hear additionally T3. Yeah, and it's a coin toss. It's like with Bernoulli gates. It's tossing coins. Which of these two outputs, T1 and or T3, will get the hit, the beat of T2. Let me even make it visible. So the blue curve is with both scopes, but I have to use the same time. Let's say 270 here and 270 here. So, all right. So what we see now is the basic sequence, the basic rhythm here at T2, and now the pink curve. This is now T3, and this pink curve is going to be T1, and we hear and see the tone cos. The high-pitched note is the basic rhythm. Every single beat, bang, 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 and the middle pitch is T1, and the low bass pitch is T3. The rate knob here, you may have expected it, sets the frequency, the speed, the tempo of the basic rate. But let me talk about this. I zoom in again, at least a bit. Let me talk about the first of these shiny little groups. The button below the rate knob, here, this button, and the LEDs show the mode. The mode, or better said, the range of the speed of the tempo. With yellow, it's everything is as I told you. That's the reason why there is written ×1. When I push the button and I go to red, everything is multiplied by 4, so you get quite fast rhythms. And when I push the button once again, I come to the green mode, and then everything is divided by 4. So things get really slowly. All right, let me return to the yellow mode, the basic rhythm. Okay, the bias knob here. The bias knob sets the probability of how often T1 and how often T3 puts out one of the gates of the basic sequence. So when I turn it slowly counterclockwise to the left, the probability that T1, this one here, gets the hit, gets the advantage of the Tolenkos is higher, and when I put it to the other side clockwise, then it's T3 getting more of the cake until it's only T3, or the other way around, only T1 which gets outputs. So now here in the middle, the probability is the same for both. The probability, not the real action. That's still the Tolenkos. There are 3 different modes of. No, let me first show and explain jitter. Jitter, let's say, the amount of drunkenness of the drummer. Well, yes, jitter acts at irregularity. Here and there, different beats and going out of the beat. Let me explain. Let me show it. Until I completely destroy regular beats. Okay. Let me return to no jitter at all. All right, so different modes. I was on my way to explain different modes of probability. These modes here, this group of 1 button and 3 different colored LEDs. The green mode, that is what we are in now and what we have been in all the time, well, that it's exactly what I have explained so far. In the orange mode, or orange or yellow or what it is, let me push the button once, then things get different. In this mode, the rate of the basic sequence at T2 is multiplied and divided by a random number, which then triggers the wing outputs. And this mode leads to the same rhythmic outputs on both wing outputs, both T's, T1 and T3, with bias in the center position, as it is now. With bias turned to the right, let me do so. The basic sequence is multiplied for output T3. So the bass here, we hear it more often, and divided for T1. So we hear it less often. And with the bias knob turned to the left, it's different. Yeah, it's multiplied. The basic sequence here at T2, which is unchanged so far, is multiplied for T1 and divided for T3, but it's the multiplication and the division by a random number always. Now to the red mode. So let me turn to bias in the middle. In the red mode, both wing outputs are triggered alternating with the bias knob in the middle. The bias knob determines how often the corresponding output puts out a gate before it's the turn of the other one. So now it's 1, 1, 1, 1. Now I turn the bias knob to the left. So it's more often that the T1 puts something out when it's triggered than the T2 up to extremes. So what's the difference to the green mode? The difference to the green mode is that which turns, which is whose? No, which is wonderful. Whose turn it is alternating. Bong, bong, one, left, right, left, right, left, right. But how long the turn lasts? So how many of the hits fall to this side? That is depending on the position of the bias knob. Whereas in the green mode, let me return to this green default mode, it's the probability itself which is set between these two sides. Instead of using the internal clock, what we have done so far, here we can clock with an external clock source. Bias, rate, and jitter have all three have their own CV input, so we can modulate them by external sources. Okay, now for the CV domain here on the right side. The process, this CV domain generates three different random voltages at the output X1, X2 and X3. The process of generating a new random voltage is clocked by the internal clock or by an external clock which is patched here into the time domain external clock input. This external clock or the internal clock concerning the time domain is independent and work independently from what I eventually put and patch into the clock input on the CV domain now. So there we can have two different clocks. So the probabilities which I have set here and the jitter settings, they both influence, or they both, better said, even determine the rate at which new random voltage is generated here at the right side. The output of T1 triggers X1. The output of T2 triggers triggers X2, and the output of T3 triggers X3. So we don't have to patch anything between the two sides, the two sides of marbles, called the random sampler here. Let me show this. I patch X1 to the volt per octave input of this basal, and X2 the same with this basal here above, and X3 to the basal here on the right side. So I have now three different rhythms and three different randomly generated pitches, but I remove them again, at least for a while. So and so. All right. I want to use only one. Let me use the middle one, x2, and let me use it with the bezier here above. And I fade out both the other twos. But I reduce the frequency offset. So, all right. The probability I have set, and we can change, yes, we can change the maximum width of the output voltage range with the button above the steps knob. So with this button here. So the range of possible voltages can be changed. Green means a range from 0 to plus 5 volt. No, to plus 2 volts. Yeah, green means a range from 0 volts to plus 2 volts. Let me change to right. Orange or yellow means a range from 0 to plus 5 volts. Yeah, so the range of possible frequencies is wider now. And last, red means the widest range from minus 5 volt to plus 5 volt. Default is green from 0 to plus 2 volt. The spread knob sets the probability of the occurrence of the random voltages in certain regions of this range. Let me choose the range from minus 5 volts to plus 5 volts. With the spread knob in the middle, I get a bell curve, a bell shape, meaning most of the frequencies are in the middle, around 0 in this time. Yeah, not in this time, in this case, because I have chosen minus 5 volt to plus 5 volt. When I turn the knob to counterclockwise, the bell shape gets narrower and narrower until there is generated only the center frequency itself. So this is only the center frequency of the range which I have chosen. So, and when I change the range, of course, the center frequency changes as well. Let me perhaps stay in the green. No. Yeah, that's better. So I go back to. So when I turn it up again here, this knob, the bell shape gets wider and wider and wider. Okay. When I turn the knob to the other side, let's say to the 2 o'clock position, all frequencies of the selected range are equally likely to occur. So now the probability of occurring is for the whole range, or for all frequencies in the chosen range, the same. When I turn it fully clockwise, so like this one, then only 2 different frequencies occur, and these frequencies are the highest and the lowest frequency of the selected range. Now I turn it up again, so the probability that frequencies near the borders occur is very high now, but not only the highest and the lowest. And the more I approach the 2 o'clock position, the more equally spread is the probability across the whole range. At middle position I have my bell curve again, bell curve of probability, with, let's say, slightly centered to the middle of the range. Okay, the function of the bias knob in this CV domain, here this bias knob, may well be misunderstood from time to time. Fact is that it does not offset the voltages which are randomly generated, but the process of random decisions. The offset concerns the process, how the random decisions are made. It's not a voltage offset. So what does this mean? It means that with position from 12 o'clock further clockwise, this way, the probability of the occurrence of nodes nearer to the upper end of the selected range, and according to the adjustment of the spread knob, increases. And with the knob further counterclockwise, here, the occurrence of nodes nearer to the lower end of this range increases. So, now it's equal, and now it's extremely likely that we get frequencies at the upper end of the selected range. Depends on what I have said about the spread knob, bell curve, and so on. And now turning it the other way around, lower frequencies at the lower end are more likely to occur. Let me put it to 12 o'clock position again. Let's go to the steps knob. The steps knob executes different functions, depending on whether it's turned clockwise or counterclockwise. At the 12 o'clock position, it's a normal position. It's the default position. We get an ordinary sample and hold function. Turning the knob counterclockwise, the edges get smoother and smoother, a kind of slew. Let me show this. We don't need these signals here, but I would like to show you the output jumps. So, alright, so now I turn the clock from the 12 o'clock position counterclockwise. And you see and hear we get more and more slew. I can't help you using a little bit of reverb. Going back again. All right, but let's exclude the reverb again. Turning the knob to the other way, turning the knob clockwise from 12 o'clock away, we force the generated CV to CVs corresponding to a chromatic scale. So a completely different function. And when I turn the further, now I have nearly the complete chromatic scale. The probabilities, of course, it's not playing the scale. When I now turn the knob further, this scale loses more and more notes until at the extreme rightmost position we have only the bass note of the scale in different octaves though. Okay, let me turn it back again. And more notes of the scale return. And now there is no scale at all anymore at 12 o'clock. There are three modes of, let's say, flavors of randomness, which we can choose with the button in the upper right corner of the module. This is this one here. The green mode, which is, let's see, here. The green mode, in the green mode, all three X output channels follow the settings on the control panel. These settings here, all three follow the steps, bias, and spread settings in the way I have, which I have explained. In the orange, or let me change it, in the orange or yellow mode, only the output channel X2, this here in the middle, follows the settings. The other two outputs take values opposite to X2. It is as if all knobs were turned into the opposite direction of their actual adjustment, mirrored along the vertical axis. So, for example, let me say, so this one. And now let's have a look at X1. And you see, X1 is still jumpy, no slew at all. Let's listen to it even. But it's forced to the bass note of the scale, of the chromatic scale, because X1 acts as if this step knob would be the other way around. And the same is with X3. So let me go back to the further onto the next mode. Now we are in the red mode. Yes, in the red mode, X1 follows the adjustments as they really are. X1 follows the adjustments as we have them here. But let me go back to steps again. And let me remove or fade out this X1. X1 follows what I've adjusted here on the front panel. And X3 reacts opposite, so meaning opposite to what is on the panel opposite. Now it's the same because everything is at 12 o'clock, but with steps it's, as I explained before with X1, now it's the same with X3, sorry. So X3, blah, blah, blah. X3 acts as if steps were this way around, as I demonstrated it with X1 some minutes ago. And what about X2? X2 reacts as if all knobs were at 12 o'clock position, what they really are. So let me change this. So X1 follows these settings. X2 acts as if all were at 12 o'clock. And X3 acts as if spread were this way, bias this way, and steps this way. All right. There is the spread CV input. The spread CV input you see here down, this is this input, but let me, for a while, silence. All right, so the spread CV input here, this way, this little input jack here, has a double function. By default, we can modulate the spread parameter, of course, feeding in an external CV source. But when we push the button below the length knob, this one here, I told you it's something special with this button. When we push this button, the module samples the CV level at this input here. Yes, and whenever a random voltage is generated by the unit, then the sampling process takes place and takes this sampled voltage as the next random voltage. I can feed in, let's say, a saw wave. Can you see it? No, you can't. So I have to, take the saw wave down and this LFO down and take the saw wave from this LFO and feed it here in. And I want X2. Oh no! I want to be in the green mode, and I'm interested only in x2. Let me listen to it. Yeah, okay. So now I push this button. And you see, and here, the random voltage which is taken follows the saw wave, because always when a new random voltage would have been taken, instead of that random voltage, it samples what is coming into this input. I can change the rate. And now I push the button again, and randomness prevails again. Now we have just randomly generated voltages again. Pushing the button again, we have sampling from this input here. Alright, I think I have told you everything what's basic about marbles or the random sampler, how is it called here in VCV-Rec. And well, I think it's clear how useful this module is for making generative music. No, I haven't. I have not told you everything, because I have not told you anything about déjà vu and things like that, the general management of randomness and loop length. So let me at first reduce the volume. Always, really always, when the module has to make a random decision, it queries the déjà vu adjustment here above. Let me perhaps zoom in again. Oh, a little bit less. View, yeah, come on. So that's enough. This déjà vu is asked with every decision the module makes, decision talking about the time base, decision talking about the CV, the random CV. All random decisions are at first, with all random decisions at first, déjà vu is asked. As long as the two buttons on the top left, here, this one and this one, are not lit, like now, for example, the déjà vu section is inactive, and everything the module does exclusively depends on the adjustments of all these knobs, which I have talked about. Okay, I have not talked about length, but I will do this in a second, or 2 or 3 or 4. Okay, but when we push one of the buttons, or both buttons, they lit in green then. You see this one and this one. Then the following influence is taken. I can activate, by the way, I can activate and deactivate the two sections, time section, déjà vu for time section, and déjà vu for the CV CV section independently from each other. So, for example, now déjà vu is not asked concerning everything about anything concerning the CV voltage. But always déjà vu is asked concerning decisions in the time domain. Now, in both domains, déjà vu has an influence. I will talk about this later. And now the time domain is independent and independently working from déjà vu. But let me activate both sides. With the déjà vu knob at 12 o'clock, like this, there is no further randomization going on, no further than what is already adjusted here and what I have talked about so far. So déjà vu doesn't do anything, and it doesn't make any changes. Let me put it like this. The module repeats the last randomly generated steps in an ever-repeating loop, and that is what déjà vu does when I switch on and activate these buttons here. And you hear it already. Yeah, perhaps you have noticed nothing changes. There's a loop going on, going on, going on, going on, going on. And what is going on? Well, it repeats the last 8 steps because I have set the loop length to 8. The last 8 randomly generated steps, randomly before I pushed the buttons. Now I can go up to 16. Or just only to 3. All right. That is with the déjà vu knob adjusted at the 12 o'clock positions. From 7 o'clock to 12 o'clock, the randomness decreases from 100% random at 7 o'clock to no further random at all. So let me go, for example, to, well, back to 8 steps. I go 7 o'clock. No changes at all. Oh, sorry, 100% random, of course. At 7 o'clock I have 100% random. Going up to 12 o'clock, as you have heard it, no changes in the sequence at all. And between, some more changes. A lot of changes, less changes, less changes, less changes, no changes at all. From 12 o'clock to the 5 o'clock position, the randomness increases from no further random, as it is now, to 100% random, like this one. Yeah, so now we have 100% randomness, and everything changes. So this means the decisions which are made stay the same. Yeah, they stay the same. But whether, for example, a decision whether or not to apply jitter and so, that stays the same. But how they are made, these changes, this changes randomly. So once again, 12 o'clock, let me put it here, so 12 with active green lit buttons here. At 12 o'clock means no randomness at all. 8 identical. The last 8 identical, randomly generated steps. The last 8 randomly generated steps repeat unchanging. From 12 o'clock to 7 o'clock, this way, the randomness increases again until 100% random, and it's the same from 12 o'clock to 5 o'clock. Yeah, I think, but now it's really everything what I have told you. Yes, that is everything what I have to tell you. And I can do this different, yes, as I said already, I can apply déjà vu only to the time dimension, or only to the, like this one, or only to the CV dimension. All right.